Yes.
And our next speaker, it is a pleasure to introduce Professor Andriy Regeta from University of Jena. The title of the talk is on the algebraic transformation groups of an algebraic variety. Please.
So I'm not a professor, but yeah, it's okay. I would like to thank the organizers for organizing this conference in such a difficult time during essentially terrorist attacks almost every day. One happened particularly today in the morning, so it was really incredible job to organize this. I like to start my talk with the definition of an affine algebraic variety, which everybody knows essentially, but nevertheless. So affine algebraic variety is just a zero set of a system of polynomials in the affine space. And here is a nice example of an affine algebraic variety. It's just a hypersurface in the 3 space. And in general, it's a very nice picture, I would say, but especially colors of Ukrainian flag make it even nicer. Nevertheless, the main affine variety is the affine space. And the group of linear automorphisms of the affine space, which is usually denoted by GLN, is a very well studied group. Here is the example of a linear transformation from C2 to C2. Today, I like to consider slightly bigger or maybe much bigger group, the group of all regular or polynomial automorphisms of Cn, of the affine space Cn. Here is the example of a regular and nonlinear transformation from C2 to C2. So this map is given by polynomials. So 2 coordinates here are polynomials, as you can see, and the inverse map to this map is also a polynomial map. So such maps are called regular or polynomial automorphisms. And basically, I'm going to study today the group of all regular automorphisms of Cn, or more generally of any affine algebraic variety. Already in dimension 2, the automorphism group of C2 is much, much larger than the group of linear automorphisms of C2, the GL2. The reason is that the automorphism group of C2 contains the following group, which I denote by G2. So this is a so-called de Jean-Pierre subgroup, which contains a subgroup of polynomials in one variable under addition. So this group G2 is already infinite dimensional, which of course implies that the whole automorphism group of C2 is infinite dimensional. Another important subgroup of the automorphism group of C2 is the group of affine transformations. And in fact, the automorphism group of C2 is the amalgamated product of these 2 groups along the intersection of these groups. So you see, despite this group is really big compared to GL2, GL2 is just 4-dimensional group and this group is infinite dimensional, we still know the generators of out C2. We know quite much about the structure of this group due to the amalgamated product structure. So this group is big on the one hand, but we know rather much about it. Starting from dimension 3, the automorphism group of Cn is a black box. We don't know the generators of this group. We know nearly nothing about the structure of this group. It's really something we know very little about. Here are some properties of the automorphous group of Cn, and basically I like to show the gap in our understanding between two-dimensional and higher dimensional cases now. So the group out C2 is very far from being simple. It contains a lot of normal subgroups besides one obvious of codimension 1. And the first example was found by Danilov long time ago. And about 10 years ago, Fortin and Lamy developed a theory using geometric group theory, so using the action of our C2 on infinite dimensional hyperbolic space. They found tons of normal subgroups. In fact, later on, Christian Ulrich showed that a simple subgroup of out C2 can be embedded into GL2C. So out C2 is really far from being simple. Nevertheless, we know nearly nothing about simplicity of the automorphic group of Cn, or rather how far it is from a simple group, so to say. Another property of the automorphous group was obtained in two-dimensional case by Julie Deserti, who proves that each automorphism of out C2 is inner up to a field automorphism. So this result was partially generalized by Kraft and Van Sten to the so-called tame automorphism group in higher dimensions. But about such a thing in higher dimension for the whole automorphism group, again, we know nearly nothing. We also know the maximal solvable subgroups of out C2. They are classified by Jean-Philippe Fortin, Pierre-Marie Poloni. And again, in higher dimensions, we know very, very little. The last property I list is about a strong Tits alternative. So first, let me tell you what is the strong Tits alternative. So a group G satisfies strong Tits alternative if each subgroup of G either contains a free non-commutative subgroup or contains a finite index solvable subgroup. So the automorphous group of C2 satisfies strong Tits alternative. This was proved by Stefan Lamy. And again, in higher dimensional case, we know nearly nothing about Tits alternative. I should add that there is a big ERC project now in France where people try to discover a counterexample to Tits alternative property for out Cn for higher n, but at the moment we know again, as I said, nearly nothing. So you see, I hope convinced you that there is a big gap between two-dimensional and higher dimensional cases. And today I will present some result for the in higher dimensional case and some consequences of this result. So this is my goal today. But first, let me recall some result proved by Olivier Mathieu, which he actually presented in the conference on Monday, So it's always good to recall some results which were presented already during the conference. So Olivier Mathieu found a subgroup in the automorphous group of C2 generated by two elements, which is not linear, which cannot be embedded into GLKF. Just could you please tell me, are you still here? Did I lose the connection?
No, everything is fine.
Okay, good, thank you. So again, he found an example of a finitely generated by two element subgroup, which is not linear, which cannot be embedded into GLKF for any natural K in any field F. In particular, this means that the whole automorphic group of C2 is not linear. It cannot be embedded into GLKF. In fact, this property holds more generally if you take any affine variety of dimension at least 2, then its automorphic group, if it contains two subgroups, C star and C plus, in general position, so to say, which means that these two subgroups have different invariants, then the automorphism group is not linear, since the automorphism group cannot be embedded into GLKF, again, for any K and any field F. In fact, one can say even more how different automorphic groups and algebraic groups are. So if X is an affine variety of dimension at least 2, and the connected component of our X is non-commutative, then the automorphic group is not isomorphic to an algebraic group as an absurd group. It's actually important to have here this condition that the connected component is non-commutative, because if connected component is commutative, the group still can be infinite dimensional, but it may happen that infinite dimensional group, it is not isomorphic to algebraic group as algebraic groups, so to say, or as groups with topology, but as absurd groups, they can very likely be isomorphic. There are many examples like this. So here it's very important to say that these groups are not isomorphic as absurd groups. So you see, despite these groups, the automorphic groups and algebraic groups, they have very different structure as abstract groups. Some people, including these two gentlemen here, were asking which properties of GL and C extend to the group of automorphisms and to the group of birational transformations of an algebraic variety X, in particular to affine algebraic variety X. Towards answering this question, I would like to present the following statement. So there is a natural structure of an int group on the automorphic group of an affine variety. I like to explain a little bit this infinite dimensional algebraic group structure. So consider now the set of automorphisms of Cn given by polynomials f1 and so on fn of degree less or equals than d. This set has the natural structure of an affine algebraic variety, and the whole automorphic group is, of course, a union of these finite dimensional pieces, so to say, which are algebraic varieties. And these finite dimensional pieces, they form a filtration. They form a sequence of algebraic varieties such that each element in the sequence is a closed subset in the next one. This allows us to define a topology on the automorphic group of Cn, namely a subset set in our Cn is called closed, or respectively open, if the intersection of Z with each finite dimensional piece is closed, respectively open, in this finite dimensional piece. Finally, similarly as in the case of algebraic groups, we ask that the multiplication map and the map taking the inverse is a morphism of this infinite dimensional varieties. Maybe I forgot to say here I used the notion of an int group. The full name, so to say, is infinite dimensional algebraic group. So just to make things short, people call it an int group. So our CN has a structure of an infinite dimensional algebraic group, and in fact, any, as I already said, any automorphic group of any affine variety has a structure of an int group. Now it's important to mention that this finite dimensional piece here, or I should say here, is not an algebraic group. It's very, very far from being an algebraic group. So the automorphic group of Cn cannot be presented as a union of algebraic groups. It cannot even be presented as a union of normal subvarieties. Nevertheless, for some automorphism group, it may happen that there is a filtration by algebraic subgroups. So out X may be presented as a union of algebraic subgroups. Well, the theorem here says that it may happen if and only if, so out X is a union of algebraic subgroups, Gi, if and only if this Gi are very simple. They're just semi-direct products of algebraic torus and a unipotent algebraic, commutative unipotent algebraic group. In particular, this means that the automorphic group of X can be presented as a union of algebraic varieties only if it doesn't contain SL2 or doesn't contain any semi-simple group. So this is a very specific situation and happens rather rarely. All right, so now let me compare the properties of algebraic group and the automorphic group. We all know that algebraic groups have very nice properties, but nearly nothing is known about the closed subgroups of the automorphism of an affine variety. An example is that any commutative connected algebraic group is isomorphic to a product of algebraic torus and a unipotent commutative algebraic group. So this holds over complex numbers and in fact over any field of characteristic zero algebraically closed. But until recently, we knew nothing similar to this for the subgroups of out X. So here is the result I like to present, which is in fact the main result I like to share today. Assume V is an irreducible algebraic subset of commuting automorphisms that contains the identity, then the group generated by V is a closed linear algebraic subgroup of out X. So what this means? Here is a corollary. A commutative connected closed subgroup of the automorphic group of X is a union of linear algebraic groups. So a commutative connected closed subgroup of our X is a union of algebraic groups isomorphic to this one. In a sense, it shows a big similarity between algebraic commutative connected subgroups of out X and algebraic groups. Using this theorem A, we were able to describe maximal commutative connected subgroups of the automorphic group of C3. You remember C3 is exactly the case when the life is very difficult. This theorem A, in fact, does not hold for the group of birational transformations. Here is the example. If you take the group of birational transformations of C2, it contains an algebraic subvariety of commuting birational transformations. V also contains the identity, but the group generated by V is infinite dimensional. So it's not an algebraic group. In a sense, the group of birational transformations is very far, has very different structure from the structure of the automorphism group of an affine variety. And again, since they are different with respect to the theorem A, we showed that the group of Bayes transformations essentially is, when it's reasonably big, so to say, it's essentially never isomorphic to the automorphic group of Y, of an affine variety Y. So these groups are different as abstract groups again. Now let me talk a little bit about Borel subgroups. So Borel subgroup in an algebraic group is a maximal connected solvable subgroup. If you take GLN, then the subgroup of upper triangular matrices is an example of a solvable maximal connected subgroup, of a Borel subgroup. It's a classical result that all Borel subgroups of an algebraic group are conjugate. And actually, we also know this in two-dimensional case. So in out C2, all Borel subgroups are conjugate. However, it's conjectured that in three-dimensional case, it's not the case anymore. And if we didn't make a mistake, we think we can prove this theorem, this conjecture, again using theorem A. But I still call it a conjecture just to avoid mistakes. Here is another conjecture that the derived length of a Borel subgroup B of out Cn is less than or equal to n plus 1. And if the derived length of B equals n plus 1, then such subgroups are conjugate. So all Borel subgroups which have derived length n plus 1 are conjugate. This is a conjecture which is still not proved. We think we have a proof in dimension 3, but yeah. Again, I'm not completely sure, but if this will be proved, the crucial step in the proof would be against theorem A. So theorem A is the crucial, or should be crucial, ingredient in all kind of studying the connected subgroups of the automorphism of X. Anyhow, now I like to go a little farther. I also have to speed up a little bit because the time is up. So I like to turn to the following question asked by Kraft, which asks, is an affine variety uniquely determined by its group of symmetries? So is an affine space uniquely determined by its automorphic group? And in the case of, in the algebraic geometry, we have two candidates for the group of symmetries. We have the automorphic group and the group of Bayesian transformations. Here are two results I would like to state. So the first one says that the affine space is uniquely determined up to Bayesian equivalence among n-dimensional varieties by its group of Bayesian transformations. When, again, it's uniquely determined by its group by the group of Bayesian transformations seen as an abstract group here. On the other hand, if we look at the automorphic group of Cn, then the affine space is determined by its automorphic group as an int group among all connected affine varieties. So this result here is proved by Kraft, and it's very nice besides this condition here, that the groups should be isomorphic as int groups. And basically, we can remove this condition using theorem A, I presented above. That's one of the points why the theorem A is useful for us. Okay, I realize that I don't have much time anymore, so I just can say maybe is that we generalize the theorem of Kraft, again, based on theorem A I presented above. So we removed here the condition of an int group and prove the theorem when the groups are isomorphic only as abstract groups. And we proved it not only for the affine space, but for any spherical affine variety. I think I should stop here since time is up, and maybe if there is a question, I am very happy to answer.